Zoom recording. Thanks again for joining us this morning. So I've been talking code officials across the state of Texas and trying to in Oklahoma to require ACCA's residential system design review form at permit for residential construction. And I'm happy to tell you that this morning, Wes Davis himself with ACCA, who basically wrote the forms. He's their director of technical services. He oversees all their technical manuals. He serves on all the technical committees. He's helped develop several ANSI standards. Really sharp guy, knows his stuff. Most importantly, in my book, you can't trust a guy that never actually did the work. Well, he is a former mechanical contractor. So he's done the work. He knows what works. He knows that JS&D do work if used correctly in the field. So we're going to be going over with the fine-tooth comb this understanding and using the design review form. Going over it line by line may be a little clunky. I do have a few intro slides. 3 or 4 of them are the same as last week's webinar, but they're important. But it's just a handful of intro slides. So let's get started. Thank you, ACCA, for sponsoring the presentation, TACA for helping promote it, and ACCA for lending us Wes Davis, and their quality assured program and materials is great. And I'm going to show you some videos and some other resources that ACCA has and that SPEAR has developed. SPEAR, one of everybody probably knows on the webinar, we serve Texas and Oklahoma, Regional Energy Efficiency Organization. Great thing about SPEAR, price is right, it's free. Any way I can help you, your builders, your contractors, you need some QA, QC, of third-party energy inspectors, whatever it may be, let me know. I'm happy to help you out. So back to this. So hopefully everybody's on now. Yeah, I've seen about 30 more people join since we started. So those folks that just joined, if you will Google ACCA Residential System Design Review Form, it'll be a lot easier to follow along with the presentation this morning if you at least have page 1 printed off of the understanding and using the HVAC design review form. I'll show you what it looks like. When you Google it, you'll have several options to choose from. Let's get back to where we were. The one you want to click on, this would be the link you click on, which is this right here. So if you Google it, depending on your browser, but the hyperlink's going to say downloads-public files-ACCA. And then when you click on that link, you're going to come to this, which is the Residential Design Review Forms and Examples. This is what we're going to be going over this morning, and specifically this understanding and using the System Design Review Form. So if you click on that, this will come up. And if you could at least print page 1, ideally go ahead and print the whole thing, but if you could at least print page 1, then as we're going through these 38 blanks, you can reference back to page 1 where where it is on the form and what it says. So I'll give you just a second to print that as I finish introducing this. So what we're going to do this morning, basically, I mean, we know that ACCA manuals JS&D are referenced and required. So this form provides basically a quick and easy review for the plan reviewer of the HVAC system design. The form gives an objective indication whether the required processes are followed. Those required processes, manual J load calculations, which, making sure the estimates are correct for the heating and cooling required for the residents. Manual S equipment selection, making sure the equipment selected is based on the heating and cooling loads and the OEM performance data and is within the maximum sizing and minimum sizing requirements. And then on the manual D duct systems, hey, are the ducts sized based on the equipment selected, the geometry, the fittings, the duct materials used? Those things all work in conjunction to form an effective, efficient HVAC system. Now, can an HVAC system cool a house with an undersized return, saggy leaking ducts? And yeah, as long as it's 2 tons oversized, which is kind of the lots of folks' rules of thumb in Texas, which worked better 25 years ago than it does today. As our envelopes get better, our windows are better. All of the 2015 Energy Code is a pretty stringent envelope, so we really need to be utilizing this form at permit. The form is meant to be So just so you know, yes, this is in the IRC. So as a code official, you are more than within your jurisdiction, and code, you know, it's straight out of the IRC. Says, hey, use ACCA Manual S for selecting the equipment based on the Manual J loads, right? Rules of thumb, not so good. And yes, Manual D is in there as well under duct design. Has to be with provisions of ACCA Manual D. Other approved methods, let's don't be approving rules of thumb when it comes to HVAC, right? So I like to leave this slide in Spanish, but all the code officials out there and HVAC contractors, to summarize this, the job you do is important. You know, if you're allowing really crummy HVAC installs with 2 tons oversized and undersized returns and saggy leaking ducts, a single mom trying to feed her kids, or a little old couple on a fixed income, that $20 or $30 a month every month that they could use to feed their kids or their prescriptions or whatever it may be. So don't underestimate the job you do, and at least have a plan in place for bringing up the industry and helping make these systems more efficient. And that's what SPEAR does. So I showed this last week as well, but just to it kind of highlights, you know, that big DOE energy code field study. Georgia, fairly similar climate. Lots of Georgia is up in the Georgia mountains. It's cooler, but you know, we're getting a whole lot less square footage per ton in Texas than we should be on a properly sized system. Typically, when you talk to folks that size systems for a living, do JS&D for a living, I've been told it's around 800 square foot per ton minimum. Again, rules of thumb don't belong in the same sentence, but if you're seeing that 4-ton unit being put in a 2,000 square foot house, I'm 99.9% certain that system's oversized. Here's those 70 observations we looked at. I think it's pretty clear on the square footage per ton. I mentioned this guy sized the unit for the 4th of July party. Works great that day. The other 364 days a year, it's grossly oversized. But I think what's of note here, of these 70 observations, you have 4 that are substantially above the rest. And I'm guessing these 4 probably did it by the book, and all of these are rules of thumb. And then, of course, our 4th of July party. Just so you know, TDLR on a total replacement of a system, if they get a comfort complaint, TDLR is going to say like for like is not a good answer on a total system replacement. You need to be doing the JS&D or JNS if you're replacing the duct as well, of course, D as well, but JNS on a total system replacement. So, you know, I mentioned the little mom, single mom, and little old couple on a fixed income. So if you are a code official on the webinar this morning and you're not requiring this form at permit, and you know, you're out there doing the rough end inspections, you know what kind of work your mechanical contractors are doing, I would encourage you to at least have a plan for improvement. I've been a building official before, so I know all too well how builders and contractors love change and loved increased enforcement. So, you know, starting to require it tomorrow might not be the most palatable and the best idea, but at least have a plan for improvement. You know, maybe in the next 3 months, you know, let all the mechanical contractors know. I mean, you can have a 1 to 2 year plan. Hey, in the next 3 months, if you're on the 1 year plan, we're going to require manual J load calculations at permit. In 3 more months, we're going to require manual S, OEM data, and proper selection to be submitted at permit. In 3 more months, we're going to require the manual D, duct design, friction rate, all of that documentation required at permit. And in 3 more months, we're going to put all that together, we're going to have it on site, and we're going to verify it. I think it'd be a lot more palatable for builders and contractors to know that, hey, basically, you've got a year before this is required, and we're going to take it in little bites, 3 months at a time. So when there's questions on manual J, we've got 3 months to get through it. When there's questions on manual S, 3, and on and on. I think you understand. That's why I used to, growing up, watching Mike Tyson knock people out was one of the highlights of my teenage years. I used to love watching those fights. That's a great quote too. But have a plan. Please have a plan for improvement. And that's the last slide. So let's get back to the form. So this form here, so the actual form itself is this. It's a one-page form, okay? And you've seen it in the resources before. This one-page form is going to ask you for attachments. You're basically going to need the J1 form, the OEM data in almost all cases, OEM data, the manual defriction rate worksheet, and the duct distribution sketch. The way this form works is these attachments and this information. So a manual J1 form is 13, 14, 15 pages long. Well, rather than reviewing all 15 pages versus the plans, we live in reality, and that code officials and plan reviewers are super busy. So this little one-page form can capture different elements of those three documents. The first little section here is based on Manual J. It's all load calculation data and inputs. This next section here is based on the equipment selection, your Manual S and your OEM data. The last section here is the duct distribution system design. So this is all Manual D. So we're going to be going through this form right here. And basically what we're going to look at is all those 38 blanks. And again, for those of you that just hopped on late, the ACCA Residential System Design Review Form, we're going to be using this understanding and using the system design review form. And if you could at least print page 1, that'll get us started. So, this form's meant to be really very simple. It's certainly neither exhaustive or exclusive. It doesn't capture everything. I mean, there's hundreds of elements in a load calculation, equipment selection, and duct design that could be verified, from the city. But this form really just is meant to examine a few items, make it simple, and it's meant to stand alone. And really, I mean, you can enforce it immediately. You could have a plan. Just start thinking about incorporating it into your new residential construction. And once your plan reviewers and inspectors really get the hang of it, I mean, you could expand it. You're certainly not limited to this form. It's meant to be completed by the contractor. And as we mentioned, it's supposed to be supported by these attached documents listed up in the top. It's impartial to any particular software developer, though the software developers that do this, they've examined the form and are incorporating simple commands that make all this align. So with all that, let's go ahead and get started. Wes, do you have any general comments or concerns, or have I already messed something up, or we moving right along?
You're doing great, Jason, as always, and thanks for inviting me to participate. I had 2 quick comments. One, you gave me a lot of credit for this, and really the credit belongs to ACCA's code committee. They're the crew that came up with this idea. They're the ones who bounced all these requirements off each other, and what's important, what do we need to do. I just happen to be the guy that kind of put it all together. So hats off to the ACCA code committee. The other thing I'd like to point out is that there's most software has a print function that will produce this form. So if your contractors are using, I think there's 2 that come to mind, but they're the largest vendors in our area, and they have a print function that will actually, if they've already done the design work, they don't have to duplicate effort. They don't have to transcribe numbers. They just hit a print function, and this will pop out. So that may help. We're talking about implementation. I think that could help promote adoption.
Fantastic. That's good information. And I forgot to neglected the housekeeping. If you have questions, just click on the Q&A. I will try to go ahead and answer questions as they go. I don't have any open questions. I did have someone raise their hand, but we've got almost 100 folks on this morning. So we'll do questions at the end as well, but if I notice them as we go, we'll do that. You will get a follow-up questionnaire from Mariel for your ICC CEUs. Simply fill out the course evaluation and you can get your ICC CEUs. So with that, let's go ahead and get started looking at these blanks. So the way this supplemental document works is each of these blanks in the form that we mentioned that should be required at permit, which is this one, right? Each of these blanks are numbered. And so we're going to go number by number and look at where you get this information, why the information. So let's get started. There's something interesting on this little section right here, but I'm going to save that for a poll question at the end. Actually, let's go ahead and do a poll right now. I would be curious if you require a copy of Manual J at permit, yes or no? Wow, a lot more folks than I was expecting. We must have a lot of El Paso folks on here, and
it's the cream of the crop, Jason.
Do what now?
It's the cream of the crop.
Right. Well, and you do find that. I mean, when you're out teaching classes, I mean, which I spend a lot of my time doing, inevitably the builders in the classes are looking to learn and do better, the mechanical content, whatever it is, inspectors, it's the folks coming to the classes that are looking to get better. It's the folks that never go anywhere, that just want to stay the way it always has been done. And we're looking at 60-40 requiring Manual J at permit. Well, fantastic. One more question. Continue. Oh, we already answered. All right, we already asked that, didn't we? What was the? Okay, never mind. All right, let's go ahead and get started. So the HVAC load calculations can be done. There's various software companies that approve Manual J load calculations. I'd be curious. I know all of these cost money. There is a free one, coolcalc.com, does Manual J approved load calculations. Do you have any thoughts or concerns about coolcalc.com, Wes?
That's a great question. I think that CoolCalc, number one, is an approved software. We need to obviously update this form because we've got a few more folks that are currently recognized. One of the advantages that CoolCalc has is it works well in existing homes. You can enter an address and it'll walk you through the steps and it's meant to facilitate an easier process for an existing home. But as far as coming up out of the ground, looking at a set of prints, I'd have to get with CoolCalc and find out if they've got a process that allows you to manually enter that data like you would for these other software platforms that are listed.
Okay. So blank number one is simply the winter design conditions outdoor temperature. There'll be a hyperlink in the resources that are sent out after this webinar. Basically, here's some Texas cities right here. We're looking at outdoor design temperature. This is also in Appendix D of ASHRAE 90.1. So we're looking at, for example, where are we at? Lubbock. So the outdoor design temperature would be 96. And depending on where you are in Lubbock, it might be a degree or two different, depending on where you are in a city. But number one, that's where you're going to get it from. This is a free table available. Wes was nice enough to send me the link this morning for this, and this will be in the resources that you get as we go forward. So what you're going to want to make sure is in blank one, that winter outdoor design temperature aligns with what is in that table. Let's go ahead and do these questions. Results from CoolCalc are difficult to repeat, so you never know what is correct. You have to check the results. Okay, fair enough. In hindsight, second thought, we'll hold all questions to the end from now on. Do all questions at the end. It flows a little better that way. So you're going to want to make sure that it's the same as in the table. Now you might want to also check. I know, like Austin, for example, their summer design temperature has been adjusted versus what's in the table. So there might be a city or two that does have some adjustments for that. Austin should be 96, and they've adjusted it to 100. They've adjusted it 4 degrees difference. But the vast majority of cities, it will come straight out of that table that we just looked at.
Hey, Jason, real quick, the numbers that we use, are are a function of two things. One is historical data. So this wasn't what happened last year or over the course of the last 5 years. This has been weather data that they've tracked for years. And then, and it factors in the fact that we get some of the really blazing hot summers and some really frigid winters. It also has some algorithms that look out into the future, and based on a lot of climate change theory, they're factoring that in. So I know a lot of folks are concerned about that, and for those that are, this does incorporate some of those aspects. So I wanted to clarify that these values are scientifically substantiatable, if that's a word. They're confirmed, and they're a value. One other quick note is that we acknowledge that this is a specific number, and the winter could get colder and the summer could be hotter, but it's only going to happen for just a few hours over the course of a few days over the course of a year, and it won't be every year. And so this is shooting for what's reasonable and defensible for an HVAC design.
And obviously, in looking at that, right, in Lubbock, it gets hotter than 96 degrees, but only 1% of the time, right? Is that how that 1% number comes?
That is exactly right, yeah. So for 8,000 plus hours a year during the normal course of a year, it'll be 96 degrees or cooler. And for those, again, those few hours that it exceeds that number, there's a lot of things in play. I don't want to devolve too deeply into this, but just know that if you use these design conditions, you're going to have predictable comfort delivered to your customer.
That's exactly what we're trying to get. So predictable comfort can be delivered without using this, but at an energy penalty and an equipment wearing out faster penalty. And Spear, being an energy efficiency nonprofit, I'm trying to save energy. That's a lot of what I do, a lot of my daily 9 to 5. And so that's why we're going through this, is it's predictable, it will work, and ultimately it's going to save energy if you do it correctly. So blank 2, the winter indoor temperature. Manual J basically tells you, hey, in the winter, we're going to keep it 70 degrees inside, and in the summer, we're keeping it 75 degrees outside. Now, you energy code nerds like myself, you might be thinking, well, hold on now, in the standard reference design, it's saying we're going to keep it 72 in the winter. Could you talk a little bit about is there a problem with the energy code telling you to use 72 and Manual J is telling you to use 70? They both use 75 for summer, but that's apples and oranges, right? Manual J is load calculations, whereas standard reference design is energy code related based on energy cost, trying to figure what your proposed versus standard reference. Do you have any thoughts on that, Wes?
Well, Jason, I think you hit the nail on the head. There's not much more to add that. We're talking about energy modeling versus a standard that's seeking to use, if you're familiar with psychrometrics, there's a study done, and then we measured where people have the most comfort, and all people are different, but we use that research to pick 2 points, one for the summer, one for the winter, that provided the most comfort for the largest group of folks.
Okay, I'm curious. So back on this, so we're looking at indoor temperature, which is the second blank here at 70, and then on the summer design conditions, the indoor temperature is 75. If Manual J says always use that, I wonder, did y'all consider making these default? And then code officials, when you're looking at this, don't confuse energy code. Don't insist that they put 72 here, because they need to be doing this per Manual J, and Manual J says 70 and 75. I'm just curious why those aren't just defaults, or why they're allowed to be edited.
Sure, it's a good question. And Jason, the code committee kicked that around, and the thought was that we want the designer to be able to enter the value that they used. Yes, Manual J has those defaults, but just like Austin has a temperature that differs from Manual J, and Manual J is very clear, it defers to the AHJ. So if you have a different design condition and you're willing to defend that to whoever asks, then by all means, feel free to use it. Same thing for indoor conditions. If the AHJ says we want to use a different temperature, maybe they want to use 68. Whatever the value is, we wanted to offer that freedom rather than, rubber stamp a value in there. That was some of the thinking there.
Makes sense. Okay, so that's 2 and 3. Easy enough. Winter indoor temperature, summer outdoor design temperature. We know what that is from the table. The indoor temperature and winter and summer are defaults. Summer design grains. In figure 1, so on that first page, the summer design grains are 35 at 50% relative humidity. So that's tied to relative humidity, which blank 6, and which in the figure 1 that we're looking at, the summer design grains were selected at 50% relative humidity. The HVAC system designer has a discretion to select 55, 50, or 45% value for this element. I'm curious. So, is there any implement? So, we'll take El Paso and Houston. El Paso, desert dry as can be. Houston, one of the wettest places on earth. So, if we've got El Paso is using 45% a good rule of thumb, or would there be problems if we use 55% in El Paso and 45% in Houston? Or any thoughts on relative humidity and design grains in relation to those?
Right. So I think that the thing to consider here too is where that number is. This is the indoor condition. And so in El Paso or in an arid climate, you would expect that entering relative humidity to be lower. In Houston, you might expect that to be higher. So if you want to account for that, Manual J offers that flexibility.
Okay, great. And then orientation can be really super important, guys. So you always need to verify that house, especially, lots of houses, one side of them might just have one window for egress or whatever it may be. And, 80 square feet of west-facing windows is going to affect the load significant, and west-facing windows and west-facing skylights is going to affect the load tremendously different compared to 80 square feet of south-facing windows and skylights. So it's just simply looking at the cardinal direction on the front door versus what they've got listed in blank 7, and which way does it face. Do y'all break that down? Does it north, northeast, or is it just north, south, east, and west? How many different selections do you got on orientation?
Yeah, there's 8. And when we talked about orientation, we thought, hey, that's a nice, easy thing to check. We'll throw that in. It's got like you mentioned, a big impact depending on which orientation you choose. And then someone said, well, orientation of what? And I know what I meant. You know what I meant, surely. But that's when we said, well, okay, let's pick a place. And every house has a front door, so we'll go with the front door. So little note on that.
Fair enough. And I could see a house where anyway, we won't beat that up. We got to get through 38 blanks and we're on number 8. So number 8, real simple, number of bedrooms. You verify the number of bedrooms. And another good reason to have this printed out, if you'll notice, these figures are all numbered, and there's 20 total figures throughout this form. So as we look at some of these things, if you have it printed out, it'll be real easy to look at the figure and follow along a little easier. This just by the nature of what we're doing this morning, I realize this is a little difficult to follow along, but hopefully we can figure it out. Again, occupants, real simple. Number of bedrooms plus 1. We've got 3 bedrooms here, so there's 4 occupants. I'd be curious, so Wes Davis hits the lottery and is going to build his forever home, and he's going to build a 8-bedroom, 19-bathroom house that just him and his wife are going to live in. Should he use 9 occupants in that 8-bedroom, or knowing that him and his wife are moving in their forever home, should he use 3?
Yeah, the great thing about forever homes is West Davis isn't forever. So I think that house is going to be around a lot longer, even if I do live there for a long time. And then what happens next? Who moves in after Wes is gone? These are some tough questions that when the committee that was doing Manual J, was discussing this, we had to put down a stake somewhere. And if you go to 9 out of 10 homes that has a family in it, you've got 2.4 kids and mom and dad. And so we went with number of bedrooms plus one. Mom and dad are in the master suite, and every other bedroom's got a person in it.
And I would assume in your New York cities or Hong Kong or Mexico City and some highly dense areas where they know that there's multiple folks sleeping in a bedroom that could, anyway, we're not going to beat that up as either because
exactly. And again, we're talking about a set of plans. We're talking about a new house coming up out of the ground. We have to make some default assumptions. If you go to visit a house and, it's a 3 or 4 bedroom house and grandma's the only person living there, you still need to model it with that number of bedrooms plus one, because as much as I love grandma, she's not going to be there forever. So sticking with the defaults in this instance is the best guidance.
Okay. And blank 11 is window overhang. I did have, was curious about this. So, typically you've got a 18-inch, 16, 18, 2-foot overhang. But what about, so basically what this says is, hey, for window overhang, you're using the biggest overhang. Is that correct?
Right. This gets back to something that, happened with the orientation. All right. So we're talking about window overhang. Which window? And so the general guidance is, number one, just make sure it was accounted for. If this house has overhangs, let's make sure that they were used. And if you have to pick one, well, then let's pick one where it's predominant. So if I've got a lot of windows, and it just so happens I've got it happens to be on the side of the house that has overhang, then let's account for that in the calculation.
Okay, I'd be curious. So with that, say for instance, I know when I was building official in Granbury, a lot of the houses built on the lake, for example, that back wall would be 60% glass, but it would be on a 12-foot overhang back porch.
Yeah.
So most of the glass is on a 12-foot overhang, but what happens when that's facing south and I've got a 16-inch overhang on the east? Does that window overhang include porches? I mean, would you want to have 12-foot listed as your window overhang in that scenario? Or is that basically just the rest of the soffit corners?
Sure. No, I think that this gets back to another key element that the committee considered, and that is, let's have that conversation. I mean, if you see 0 overhang, then that should spark a concern. If you see 12-foot overhang, maybe that sparks a question. And you look, do I have a covered porch? Okay, well then it looks like he took this into consideration. But if I see 0, well then I'm looking at the elevations. Do I have overhang? Yes. Is it on the second floor, and therefore this first floor window doesn't have the benefit of that overhang? Okay, but it's meant to spark the conversation. So if you see 0 or you see some other number, then take a look and see what makes sense. And again, getting back to sort of a fundamental principle, we wanted it to be something that a code official could quickly and easily check. So the design conditions, we make that available. Overhang, they can look at the elevations and say, hey, this house has some overhang, and there's some windows that ought to have some overhang represented in load. And you can have that conversation with the designer, with the contractor.
Okay, great. Blank 12, windows internal shade. Basically, if I understand this correctly, the software is going to assume that, hey, we're not just going to not have any sort of shade whatsoever. That solar heat gain is going to be tempered by at least something. And so the default value is basically what they're saying is, hey, we've got a medium color blind slats at 45-degree angle. Is that again just something to kind of look at and make sure there's something nothing crazy listed in there? How
Right.
important is that?
Right. And or did they use the default? Unless I've got a house on the lake and I've got a big picture window and that's purpose-built daylight window. My intention is to never cover that up. I want to have that view of the lake or the mountains or the whatever. But every other house is going to look a lot, or every other window in the house is going to look like that illustration you've got showing up. There's going to be some blinds probably, and they're going to probably be about 45 degrees. And this shows the blind covering the whole window. The default value in Manual J is 50% coverage. So I think if we all got in our cars and we're driving to our next inspection, we look out and just at the windows as we drive down the street, we're going to see something like this. And so this was the default value. The designer has the option to make it more stringent, or if you're an existing home, you can add what you find. If I see drapes, you could add those drapes and take credit for that as well.
What about where does, if the windows have screens or not, come into play? Does that come into play?
It does, and that's another default value, the external shading. There's an insect screen adjustment, and again, there's a default value for that. We didn't want to get too deep a dive on the windows, so we didn't hit on that. In fact, the next item, skylights, we didn't want to get into solar heat gain coefficients or slope of the roof. It's important enough. Did they at least account for it? If there's a skylight on the plan, did they account for it? Because if they didn't, there's going to be a big problem. And so we wanted to keep it simple.
And that's the great thing about this form, and that's why I've been encouraging it for years. Is it's a one-page form, guys. You need a one-page form at permit, and you can't capture everything in that one-page form, but you captured the important stuff, and you captured enough to know. I know in talking with the chief plan reviewer for the city of El Paso, he says we look at 10 items. We look at 10 of those 38, and we kind of rotate the 10, and it kind of keeps, just keeping people honest, and again, bringing up the bottom of the industry in general so that everybody can get a better, properly
sized. That's a good idea. Yeah.
So total heat loss, sensible heat gain, latent heat gain, and total heat gain. This is kind of what it's all about. This is the crux of the argument. This is where we're selecting and designing and installing based on all of this. This is what Manual J is going to ultimately kick out. I know, a lot of manufacturers might not list the latent capacity, but they'll list the total capacity and the sensible. It's as simple as subtracting one from the other to get that. Any other comments or about now, and on Manual J, if you're entering the heat gain for each of those rooms, well, at the bottom of Manual J, and I've never done a Manual J, I'm just being honest, I never have. I've played around on CoolCalc some, but I've never done it just from start to finish on any software. I know certainly plenty of folks that have. On the, that bottom total heat gain number that's based on that room by room loads, is that not a spreadsheet? I mean, is there a reason to go back and double check that those are, does the contractor himself do the addition and punch in that number, or does that column automatically calculate that based on the individual cells as they're filled in? That?
Yeah. So Jason, I think if I was a code official and someone brought me this form along with a stack of worksheets they'd filled out by hand, yeah, I might be checking the math. But
okay.
By and large, the software does the addition and subtraction, the multiplication, and all the math for you. If you feel the need or desire to delve into that, you are more than welcome to. Again, we wanted to provide something that would start a conversation. And so if you saw a really weird number, like a very high latent gain in a very arid climate, you have that conversation. Or if you see little or no latent gain and you're in a very humid climate, hey, let's what happened here?
Makes sense. And that's just so those of you that know, here's kind of what that Form J1 looks like in a manual J. You've got all the windows, skylights, wood, doors, walls. All of these will have heating and sensible cooling. And then this is it. Like Wes said, if you get this written out on a bar napkin, yeah, double check the math. But if you're getting a printout from the software, then there's no reason to double check this math. It will calculate based on the column. All right, on to section 2. What I've been told is kind of a little bit of the art of the HVAC world, whereas manual J is kind of the science. It's just simple. Well, there's a little bit of art in all of it, but the equipment selection is, I've been told, is kind of well, they're all important, but this is as important as any. Now, the equipment sizing requirements come at Manual S. You know, the IRC basically says use Manual S, and this is what Manual S says on equipment sizing limitations. Basically, you can oversize the heating side of it about 40%, 100 to 140% of the total heating load. Air conditioners, there is a 15% oversizing allowance built in, so there's no reason to add a ton, as folks like to do. That's already built in. We already looked at the design temperature. We already know there's fudge factors built in all through this. So adding an additional half ton or ton at the end is certainly not necessary. Now on cooling, I notice on cooling dominant climates and heating dominant climates. In climate zones 2 and 3 in Texas, those are always going to be cooling dominant climates, I have to assume. But looking here at Pampa in climate zone 4, Pampa, Texas, is that cooling versus heating climate zone delineation? Is that simply a ratio of heating degree days versus cooling degree days? And once you get more heating degree days, are you a heating dominant climate? Is that how that works, Wes?
So the short answer is yes. That is the delineation. Those are heating degree days, and that's typically days. I'm trying to remember the number. What? Go back to that chart for a minute,
okay,
Jason. 65 and 50, and these numbers. I'm aware of time, so I'll try and keep it very simple. In fact, I will. Yes, this is a ratio of heating dominant versus cooling dominant, and the number we're looking at now is 2. So if you are a heating dominant climate, that number, like for Pampa, would be above 2. And if you go up to climate zone, so probably north of climate zone 5 or so, you'll see a lot more heating degree ratio of 2 and higher.
Okay, so that ratio needs to be 2 for it to be heating dominant.
Yes, sir. That's the one.
Okay. Okay, great. So in Texas and Oklahoma, it's 115% of the total cooling load. Notice the little asterisk there. We'll talk about that more as we go. So under the OEM and Manual S section, blank 18 is simply equipment type. In Texas, you're going to have a whole lot of gas furnaces listed there. Hopefully it's either gas furnace or heat pump. Hopefully we don't have, electric strip resistance heat only for heat. It really, in Texas, a heat pump's going to pay for itself pretty quick. Blank 19, hey, we need to know the model number, because ultimately that model number, which is here, we're going to want to compare that model number with the OEM data and make sure that these BTUs align with that ratio. So back to the form itself, hopefully you've printed this and can follow along. But back at this form, what are we looking at? We're looking at a total heat loss of 59,000 BTUs, and we're allowed 40% oversize. So 59,000 BTUs, and then heat gains 27,000 BTUs. So we go back to this, and this is why I said follow along. And if we've got 59,000 required and we're at 64, we're within these design conditions, right? So that's what you're going to want to look. And when y'all develop this form, did you think about if they entered those numbers such that it was above the 40 and 15%, highlighting it in red, or some sort of indication that, hey, this is outside the parameters of the sizing limitations of Manual S? Is that, did that come across y'all's minds on that?
You know what, Jason? This is why we like to participate with SPEAR. We get these great ideas, recommendations. That's very smart. I'll take that back to the committee. It'd be nice to have a very simple, hey, this passes. We did the math. It's within the tolerance. So I'm writing that one down.
Or just highlight the number in red or something. Great. Well, hey, look at there. We're working hand in hand. All right,
Absolutely.
fantastic. All right, so multi-stage equipment. Multi-stage equipment is going to have more than one capacity level. So you're not going to look at the first stage BTUs. So that first stage BTUs on a gas furnace right here, 48,000. You're going to look at both stages, add them together. And that's what's going to have to fall into that 100 to 140% requirement. Is there, I'm just curious on that. Well, let's move on to cooling as we're running out.
Sounds like we're doing another webinar on this, Jason.
Yeah, I think we're probably going to need to, and getting through those illustrated examples will help as well. Now, of course, heat pumps are different, significantly different, and example 2 does go through a heat pump. Maybe if this webinar, if we get good evaluations and folks want, maybe I can coerce Wes into coming back and going through the 2 examples that correlate to this form. But just for just keeping it simple, heat pumps are different, and you're looking at the heating capacity of the heat pump side plus the electric resistance that, a heat pump's not going to be able to keep a house warm if it's 4 degrees below zero. I mean, there's certainly the manufacturers, they've gotten them a lot better, but heat pumps installed in Houston, Texas or San Antonio on a super, super cold day, that heat pump is typically not going to be able to keep up. And so on that heating output capacity, you're going to want to make sure it's the heat pump capacity plus the strip capacity. Is that the right way to say that, Wes?
That is, yep. And or if you're using a hybrid or a dual fuel system, you've got a heat pump and a furnace, then there'd be a switchover point where you'll stop the heat pump from working because you don't want them working at the same time. That has a very negative impact on the refrigeration circuit.
Is there so I know the energy code requires a lockout on the heat strip when the heating load can be handled by the heat pump. So you're saying if the heat pump's running and the strip heat's running at the same time, what does that do to the equipment? And why don't the manufacturers keep that from happening?
Right. No, I'm talking about the furnace. The furnace,
oh, okay.
If a furnace is running and that heat pump tries to run too, now I've got that preheated air. Typically, the furnace heat exchanger is before the refrigeration circuit coil, the indoor coil. And so if I get that superheated air going across that coil, that's going to wreak havoc on my compressor.
Gotcha. Okay. Yeah, you can tell I've never been an HVAC
contractor.
Yeah,
I'm sorry if that wasn't clear at the beginning. Yeah, heat pumps and strip heat are made to work together. That's a match made in heaven.
Okay. So you're looking at, as a code official, that blank 20 and 21, the heating output capacity, which would be the heat, if it is a heat pump, and then the 21 would be the supplemental heating capacity. Those two added together, that's got to fall within that 140% parameter requirement that we talked about. So let's look at cooling equipment data, which is really 90% of what we're concerned about here in Texas. We can all handle being a little cold in the winter, but oh my goodness, you better keep it cool in the summer. Blank 22, simple. Hey, what are we putting in? Air, heat pump. What's the equipment type for the cooling? Well, it's going to be an air conditioner. 23 model. Again, we're going to need to be able to look at that model and the data from that model with the OEM data and making sure that the the BTUs and fan speed, all the things align that we're looking at. We'll get into fan speed and static pressure and all that in the manual D side. Sensible, latent, and total cooling capacity. Just generally, when you talk sensible versus latent, they're just a 101 difference, why it's important, and the total cooling real quick.
Well, absolutely. And so the sensible heat, the best way to think about that is what you would see if you were looking at your thermostat. What's that temperature? That's a sensible value. If you held out a thermometer, the value it read would be what we refer to as the sensible heat. The latent heat is this sort of hidden heat, and the folks in humid climates know that a lot more than the folks out in the dry part of the country. So when it's humid, that moisture is in the air, and you can't see it. You can certainly feel it, but that's the moisture in the air is the latent heat. And when you add those two together, then you get that total heat loss.
And then where manual S allows you to add half the excess latent capacity to the sensible capacity if the sensible capacity is insufficient, does that in all reality kind of lead to allowing greater than that 15% oversizing, or could you expand on that just a little bit?
Sure. So the sizing tolerance deals with the total capacity. And this gets to the point you made earlier about the art of this. It's knowing how to use science and use the math to your advantage. And typically when an air conditioner starts up, it works on that latent load in the house before it starts lowering the temperature. So it's working to remove the moisture before it starts to lower the temperature. And that's why, well, again, I don't want to get too deep into the science, but as the system works and that latent load comes down, then the system's able to deliver more sensible capacity. It's able to lower the temperature more. And that's why there's this principle that Hank Rakowski, the author of the manual, put in, that if you can add half of that latent capacity, excess capacity, to the sensible load, because that's just the way, the nature of a direct exchange, a DX cooling system. That's just the way it works. It'll have that extra capacity.
Makes total sense. All right. So I noticed on the manufacturer stuff, we're selecting that 63.
Yeah.
On the example, you want to, is there anything worth discussing here on this key element information source table while we're looking at it?
There's a ton, but I'm looking at the clock, and
we can go over a little bit. We're gonna run over. We're gonna be 10 minutes over. That's okay. I'd rather run 10 or 15 minutes over than cut it short. So go ahead.
Sure. Okay. Well, this becomes a factor mostly when you're reading the performance data. And again, depending on the level that you as a code official want to delve into what the contractor provides you with that OEM performance data, this will help you know what values they used or should have used. And I think Jason's going to get into the forms themselves, the OEM performance data. But these are the key points that you'll need to know when you're determining what that system can use. So if you're checking behind the contractor, maybe it's their first time doing this and they're not that familiar with it, you can see what values they used and determine, hey, you know what, they got it right. They either got the number exactly right, or maybe they're in the ballpark, but hey, let me walk you through this. Let me show you how this works. And so the outdoor entering condition, for those that have printed it out, you'll notice that there's two examples. Jason's showing one now. There's another one down below it. And the point of that was to say that there are a number of ways that manufacturers present this data. And so the point is to, we provided a couple of examples, but the point is that those key elements are in all of them. What's the outdoor dry bulb temperature? How is this system working? in a milder climate, or is it in a really hot climate? The indoor wet bulb, what's that condition as it comes in? We talked earlier about the 55, 50, and 45. What do we think that entering condition is going to be? And then the indoor dry bulb, that's the 75 that we specify. And unless an authority having jurisdiction specifies a different value, that's the one that should be plugged in. And then the airflow. And all of those factors play into how much cooling that system can deliver. And the example Jason's showing, when you plug all that in, this system is going to kick out 21,200 BTUs of sensible capacity. And if you look to the left, you see the total capacity. And so 28.7 minus 21.2, that's what, 7.5? That's 7,500 BTUs of latent capacity. And that's, this format's pretty typical of how manufacturers will present it. They'll say, here's the total, and they'll either have a sensible value next to it, or they may have a percentage. And they'll say the sensible heat ratio is 0.8. And so you'd multiply 0.8 times that total capacity, 28,700. There's, depending on your climate, you want higher airflow. If you're in an arid climate, you only need that sensible capacity. And you'll notice that the drier the air, or on the entering wet bulb value, the smaller the number, the higher the sensible capacity. In fact, in this example that we're looking at now, if I see the 57 degree entering air temperature, reading across the total capacity and sensible capacity for all three temperatures is exactly the same. So at a higher airflow, that's going to be the same number. We only need sensible capacity. Let's turn that fan up. If I'm in Houston or in a humid climate, I need to wring the water out. Well, then I might use a lower airflow and use that 875, and then you'll see that there's a lot more latent capacity that becomes available. So I think I feel myself droning on here a little bit, Jason. I don't want to get too lost in the weeds.
No, it's great. It's great information. And as long as you have 15 extra minutes this morning, I hate to just.
Yeah, happy.
Okay, great. Fantastic. Because this is too good. I don't want to stop until we get through it. And I do want to get to what you've prepared as well. So
sure.
we're going to go a little over this morning. So now, multi-stage air conditioning units, just so these are just examples of multi-stage units, what they can handle if it's running at first stage or second stage. Is there efficiency? And now I understand we want to do JS&D 100% by the book, but just some like general thoughts on what about the HVAC contractor that says, well, I got a multi-stage unit, so oversizing doesn't matter because it's just going to run at the first stage, and it's actually going to save you more energy being oversized because it's just going to run at the first stage all the time except for your 4th of July party. Can you talk a little bit about multi-stage units and that thought process?
Yeah, sure. Happy to. And I think that by and large, the key point, in my opinion, is what does that system actually do? I think there's a whole lot of marketing out there that talks about what it should do or what it might do, but there are studies of people who've installed variable speed systems, thinking that was going to ramp down to the lowest operating capacity and be operated at a very efficient level and bring moisture out of the air and grow hair, make you lose weight, all kinds of things. And the results were that wasn't always the case. And so that's why sizing is so important for any system you install. Number one, you don't want to pay too much. Number two, you want it to work right, not only to keep you comfortable, but to keep your house in a state of being so that it's more durable. You also don't want this system starting and stopping. And oversized systems will do that. That's just the nature of the beast. They'll come on, they'll cool or heat the space and then stop. And so oversized systems, and that's another reason, going back to the whole 1% and 99% design values, why don't we design for some extreme weather condition? Well, we're trying to minimize that equipment cycling when and where we can within a reasonable limit. So going back to what I started with, and that is, how does the system actually work? So if I've got performance data and I see that the system can, on first stage, provide cooling, and typically there's also a kilowatt value. Here's how much energy I'm going to use to deliver this many BTUs at the first stage or at the higher stage. And so when you look at that, you'll see what this system can actually do. And a lot of times the marketing language doesn't always bear up. I'll touch on one thing real quick, Jason, that is on heat pumps. There's a lot of desire to oversize a heat pump so you have that extra heating capacity. And when you oversize a heat pump, then I also oversize the cooling capacity. And Manual S does a very good job, in my opinion, of walking that or walking through that. And that's one of the reasons the whole heating degree day, cooling degree day metric was added, was to say, if you're in a heating dominant climate and you want to add extra capacity to your heat pump, here's a rule to do that. And so the 2014 version of Manual S, which came out after this checklist, and is in the might be in the 2015 code, definitely in the 2018. But it provides language so that you can add extra heating capacity without damaging or harming or hurting your customer by having too much cooling capacity and creating problems on the other end of the spectrum.
Okay, yeah, that makes sense. That's something's got to be done, especially in those climates where that's probably not too terribly worried about that in Texas, but I can see that being why that had to be dealt with for sure. Blank 27, heating CFM. So basically the volume of air required to deliver the BTUs, and we were looking at that 1,000 number based on that OEM data in that table we looked at earlier, figures 7 and 8. I noticed must have a temperature difference. It listed no less than 35 and no more than 65. Well, if we go back to the first page of the form, well, if that temperature difference can be no more than 65 and the outdoor outdoor temperature is -2 and we want to keep it 70, that's 68. Does that fall outside that 65 or am I looking at something different?
No, that's a great question, Jason. And what the temperature difference we're looking for here is, what's the temperature going into the furnace and what's the temperature coming out of the furnace across that heat exchanger, because the manufacturers set limits. And if you go up to page 5, there's one example that's on the 2-stage. They say 35 to 65. So if it's less than 35 degrees, there's a problem with condensation. If it's more than 65, then it can damage the heat exchanger. And there's typically a limit switch. They call it a high limit switch. So if you exceed that 65 degree temperature difference, and for the sake of argument, let's assume we've got 70 degree air, because that's simple math, 70 coming in plus 65 degrees of heat added, then we should see no more than 135 coming out of the supply plenum. And if it does exceed that, the manufacturer puts in a switch and says, hey, we're going to shut this furnace down, let it cool off, and then we'll try this again. This goes back to the limits with oversizing. If you put in a system that's too big and it starts tripping on a high limit or shutting itself down because the high limit switch trips, that can cause problems for the customer, problems for the contractor, problems for that OEM, for that equipment manufacturer. So that's what we're talking about there. We want to make sure we've got good airflow that promotes staying within those temperature rise limits.
Okay. Makes sense. Cooling CFM probably is similar concerns and things to think about. I read through this gray section here and had to read it a few times. Is there a summary or something with cooling CFM that we need to think about, or can you dumb this down for the folks on the webinar, or more to say about item number 28 in the form?
Sure. This we touched on a little bit. The equipment will deliver different cooling capacity at different airflow, just as it does with the different temperatures, different entering conditions. And so this, without trying to beat it up too much, is in the arid climates, you can use a higher temperature difference, and in humid climates, it's better to use a cooler temperature.
So in Houston, you know, how would a inspector, if a green HVAC contractor is out there and he sets the fan speed on high in Houston, and an inspector doesn't know how to check for that, is there a way in the field to look for that, or is that a problem in reality? I mean, setting that fan speed incorrectly, is that something that's easy to do, or ways to check that? Just more thoughts on that in general?
Yeah, this gets, so if you're in the field and you're verifying this, and if you scroll down to page 9, you'll see an example of a blower table. So this manufacturer is the XYZ Furnace Company, world famous all over Oklahoma. And here we've got a furnace, and here's the difference in how much air will be moved through the system based on how much force it has to push against. And so this is sometimes as easy as looking on the fan motor itself. There will be plugs that might be labeled A, B, C, and D. It might be H, M, and L, or some combination of letters. It may be something that's selected or done at the thermostat. I think that by and large, the thing that we're looking for, again, is, was this considered? Did the HVAC contractor walk through this process when they were designing this HVAC system? And if you're in a humid climate and you see airflows that exceed or exceed, say, 450 CFM per ton, that's a concern. If you're in a dry climate and you see low airflows, say around 350 CFM per ton or lower, that's also a problem. So I think that those are some things a code official could look for. Or if they see them, have that conversation with the contractor, understand why they decided to take that step.
Okay. And then, so those are two of the key entries here in this form: design airflow and static pressure. Well, Wed's just mentioned, hey, just make sure that those numbers look right, and hey, we're at least making sure the HVAC contractor is considering that. So that's blank 29 and 30. We're almost through the 38, and then we'll get, Wes has some additional duct, total effective lean, static pressure, some additional information on this. 31's component pressure losses, pretty self-explanatory. Basically, we're taking into account the various parts of the system. I did notice on the component pressure losses, though, is the 1490s and 745s in that flex duct run, and the 500-foot total equivalent length. Is that calculated on another side? Does that not? How come I don't see anything about 90s and adding pressure loss because of the way the duct is here? We're just looking at dampers and grills and things of that nature. Is that
right? Yeah, that's exactly, it's a great question. And so this tries to capture some of the more simple aspects and set up the calculations and set up the discussion for what happens next. So if we know that we've looked at that blower table and we're looking for a certain airflow, and that's correctly listed here, and we know that based on that airflow, the the static pressure should equal, in this case, 0.75 inches of water column. Okay, that's known. We've got the top part. Then, yep, we know we're going to have a coil, and there's going to be a filter, and we're going to have outlets and supply diffusers, return grills, and there's going to be balancing dampers installed. And there's some other things listed there. Maybe they're going to have some UV lights, or maybe they're going to have a heat pump with electric heat added. Are those things accounted for? And so with a residential HVAC system, it works almost backwards to how commercial systems are designed. With residential, we've got some fixed values. And so that's where we start. What are those fixed values? And then what are we adding to the system that will diminish the flow and increase the pressure? And so we take away the values associated with those components from the static pressure, and that leaves us with this, okay, I've got this available static pressure. Just a second. So that tees us up next for the thing you're talking about. Okay, here's what this fan has got left over for the duct system. So that's what this is all about. And then we get into what you're talking about, all the elbows and all the fittings and the transitions and the duct links, etc.
Okay. That's a Right-Soft senior trainer, Alex Meany, did a whole hour, about an hour and 20-minute webinar for us that he titled "Residential Duct Design is Backwards."
Yeah.
And you mentioned that as well. Hey, it's just not really ideal, but that's just the way it's done.
Well, in the commercial world, they consider the exact same things, but they come up with a number, and then they pick a fan, and sometimes the fan blade that will deliver the airflow to overcome all these factors. And so it's just, growing up as a contractor doing residential work, I've never selected a 3-horse motor versus a 4-horse motor, and so many blades per and the curvature, et cetera. I just grew up knowing that, hey, I've got a limited amount of capacity here. How can I best use that? So yeah, that's it. Yeah.
And then 33, 34, 35, basically you're looking for your longest, the effective length of your longest supply duct.
Yeah.
Y'all saw last week in the webinar that I gave that 12-foot and section of duct had a total equivalent length of 124 feet. So it's not just, it's the effective, that key word in quotation there. So if you see longest supply duct in blank 33, and that number is 42, that's not right. It's the effective length of the duct. You take that and blank 34, the longest return duct, and that gives you your total effective length. And I know Wes is going to expand on this in a minute, so let's go ahead and move on to the friction rate. Would it be good to get into the weeds here, or is that on your supplemental slides? Is that you want to wait and save that for that?
Well, I'm not quite sure, but
Okay.
we can dive in here, and if it is something I touch on, I'll be happy to speak up.
Okay. Well, so we know that from last week's webinar flex duct is the predominant air supply vehicle in Texas. It just is. We are all using it for new residential construction and getting that stuff stretched right and having the friction. Is there so other than the friction rate being greater than 0.6 and less than 0.18, is any other thoughts on checking that box number 34's input? And that might be another one to highlight red if it's outside of those parameters.
Right. Oh, yeah. That's very good. Let me write that down. So the short answer is no. I think if you see a very high number, that tells you that fan has to work really hard to move the air. And if energy is a concern, you really want to see something a lot lower on the curve. So if someone's touting their design as being energy efficient and they've got a very high friction rate, that's not the same thing as high static pressure, but that is a factor that's built into it. So I don't want to say they're equivalent. They're not the same number. They're not the same value. But there is some correlation between those two. And if energy efficiency is something you're looking for, then you definitely want a lower friction rate value.
Okay, great. All right, duct materials used. Hey, we're coming to 37 and 38. Basically, what are you using for the trunk? What are you using for the branches? Now, when it says trunk and branch, what if we're just using a duct board plenum and then flex duct everywhere? So
sure,
would that be flex duct trunk and flex duct branch at that point, or would it be duct board? Because it's not really a true trunk and branch. What most contractors are installing, frankly, it's an undersized plenum that doesn't follow any of the manual D guidelines, with takeoffs coming everywhere right after it starts, and top and bottom and sides and everything else. But trunk and branch, can you elaborate on that a little bit for us?
Sure. Yeah, I think that the committee wanted to allow for some flexibility while capturing the basis for the design. So if I'm using a plenum that's ductboard and running flex duct out to triangle boxes or to Ys, then that would be a flex trunk and flex branch runs. And the reason we're calling this out is so that when you are, if you've got a ductulator, if you've got a duct calculator and you're trying to spot check the sizing, then you know what material you're looking at. And so if you're using a sheet metal portion of the duct slide rule to evaluate a flex run, then you may not get the same answer that the contractor had or what's specified on the design. So that's the basis for the question, is so that you can, if so inclined, spot check some of those values.
Okay, that's what I know. The city of El Paso, for example, they do require a duct board trunk, and they're only allowed 10-foot maximum flex duct branches unless it's stamped by an engineer. That they're, you get a whole lot more certainty in the effective length on a trunk and branch versus 95% of the contractors. Again, it's an undersized duct board plenum, and for all intents and purposes, it's flex duct trunk and branch.
Yep.
So a couple of attachments, the duct distribution sketch. When you're examining that as a code official, that's supposed to be attached to this residential design review form. Are any things to double check on this? Anything? If you're seeing, 900 CFM in the master closet, obviously that's not correct, or just anything, or is that just general guidelines? Again, just to kind of make sure they're doing it, make sure they're thinking about it, make sure they're designing it appropriately. You see the different duct sizes mentioned here. Obviously, the straight lines would be a trunk, and then branches with the flex with the squiggly lines. Anything else of note on that?
No, I think that's the basic intent. Is to give you an idea. At the plan review stage, you can pull out your ductulator or duct calculator and spot check some sizes. The one word of caution that I would add is, if you get a different number, have that discussion with the contractor. There are software tools that will actually calculate the size of each branch run based on those formulas we talked about before. So when Manual D was created, Hank Rakowski, author, great guy, said, hey, we need to calculate this for every branch and every supply and every branch run. And while that's great for engineering, contractors have got other stuff to do. And so it was decided, hey, let's just take the worst case scenario and then install balancing dampers. So if the duct is too big, that's really not a problem, because I can tune that down a little bit. But with software these days, it can do all that math. And so if you look at a duct run and it's marked as an 8-inch, and you look at the CFM and you look at the friction rate, and you know what, that's supposed to be a 7-inch duct. Well, have that conversation, because if you get a drawing like this that was produced by software, then it's entirely possible that that is supposed to be an 8-inch duct, not a 7-inch duct. Let me see. There was one other point. So that's at the plan review stage. The other good thing is if you take this out at rough end, you can look and see, okay, is the layout basically like it was drawn here? I hesitate to promote a direct comparison, because sometimes framing is such that I can't put a boot there. I can't run a trunk line there. And so use this, take it with a grain of salt. And again, if necessary, have that conversation with the contractor and understand that, you know, he had to relocate the trunk because of this web truss, that system that went upstairs that he didn't know about when the plans were handed to him, or maybe some framing detail, or, you know, HVAC contractors, electricians and plumbers, we're all fighting for similar real estate, and sometimes they get there before we do. Take it with a grain of salt, but it's good to know that some consideration was given, the design was plugged in, and I think you're going to find that a lot of time there's a lot of similarity between what was drawn and what was installed.
Yeah, and just having like you said, having that general guideline in the field would be great, a great tool. I've certainly never been on an inspection where there was a duct distribution sketch on site. This is the duct sizing calculator, the ACCA's duct calculator. You dial in your friction rate, your material, duct board, what you're using. And I've never really used one of those. We could probably go for quite a bit of time on how to use that and how all that works. But as we are running the manual, I'm not even going to get to the manual J abridged checklist. I want to show real quick a couple of these resources, and then I want you to share your screen and go over what you've prepared, just so everybody knows you're going to get an email with a Word document attachment. It's got 1 page of just basic mechanical permit inspection and installation guidelines. It's going to have a 1.5 pages on myths about duct design. Lots of jurisdictions. We've got some seriously undersized returns. We've got some other issues that are based on some of these old myths. And then under the additional HVAC resources, if you don't know your design conditions, here's the link that Wes shared with me this morning, really handy. ACCA has a video series on YouTube that 3 different videos, what code officials, anyway, really great resources here. You'll be getting that on the course evaluation email. Those ACCA videos, there's a part 1, 40-minute on load calcs, 1 on equipment selection, and 1 on duct design. We also have a Spear communications channel. That link will be on the resources that you get as well. And if you want to share your screen, Wes, and finish up with that stuff you've prepared to really button up this manual D side, that would be fantastic. And we can see it.
There. Jason, did the screen show up? Is it showing the?
Yes, we're seeing it.
So this is that manual D portion. I think it's great that you guys have already covered a lot of those terms, like equivalent length and effective length. We talked about the fact that this information is pretty easy to get. We can look at the materials that were used, and that's pretty easy. But this middle part's a little bit fuzzy, and I wanted to quickly walk through it because I realize we're way over. Jason showed this illustration, and a lot of this information comes from this friction rate worksheet. So the bottom number down here, this 0.09, is what you would put on your duct calculator to size this this duct run. But to back it up, let's clean up all the stuff and just look at the duct system. To understand what size that is, we need to do this effective length worksheet. And I hated these as a contractor. I was so glad when a lot of the software vendors started doing this for me. It made my life so much better. So for the sake of argument, we look at what's, again, I talked about the longest run. Here's one that's pretty cotton picking long. That's a supply run. Here's another one that's pretty long. So looking at it, I'd say those are the longest ones we'd have to worry about. So I'm only going to focus on those two. And I'm going to name them something really hard like supply 1, supply 2, and then the return. Looking at the return, I've got this, that, and this. So that's probably my longest return. And we're looking at the path of the air from when it goes in this return through this duct to the equipment as it gets conditioned and then delivered back to the space through one of these two paths. And we got to figure out which one is which. And there's my return. So back to my effective length worksheet, there's supply 1, supply 2, return 1. And now, and Jason, I think you've already gone through a lot of this stuff, these fittings. So this is the supply plenum. So this box, and here's the equivalent length of what that fitting would look like. And I take that value, that equivalent length value, and I plug it in. Since it's going to be the same for both supply runs, I plug that number into both places. On the return, same thing. How does that air, when it enters the equipment, how does that look? What does that look like? And there's different configurations. Manual D has a big catalog of different configurations. Again, what's that equivalent length? And then I plug that in on the return side. That's how it goes in on the return. Real quick, here's 2 different supply plenums. And you'll notice this is very efficient, has a low equivalent length as opposed to something that you might see in the field, which is almost like a bullhead T, and it has a very high equivalent length. I don't want to belabor that. Just know that it's much easier to push air through this than it is through that. So I do all the math. I look at all the fittings. Oh, I got arrows and nothing to. All right, there's my plenum. There's some branch takeoffs. There's a boot. There's a much more efficient boot. Here's a radius. This is a flex duct. And so that, what's that calculation? Well, manual D has an equivalent length. Looking at the radius of the turn, this was a nice, easy bend. And so at 278, that's what supply 1 right here. That was the longest run by about 28 feet. And then the return came in at 110. And so I take those numbers, plug them in after I've looked at what's available. All right, now what do I have for the ducts? The ducts added up to 388 feet. I plugged it into the formula and have a friction rate of 0.09, so I can size these ducts based on that friction rate. That's very quick. Manually, this is a heavy lift, but software does the calculations in an instant. Don't do all that other work, estimating the heat loss, heat gain, picking a good heating and cooling system, and then trip over the finish line. And I'm done, Jason.
Okay. And so when the software, when you're looking at that longest run, so those 3 or 4 really short runs off the plenum, if you've got one super long run, and you're calculating all that based off the super long run, does that not significantly affect those little short runs, or is that just taken in?
Oh, absolutely. Yeah, it does. But if I put a balancing damper in there, then I've got a way to control that. So if I'm looking for 85 CFM here, then I can tune this 6-inch run, may move, say, 130, 140 CFM. And that's why balancing dampers are so vital. And putting those in, or again, if I'm using software and this effective length has been calculated, this might be a 5-inch flex duct. So it just depends on what you're doing and the tools that you're using.
That makes sense. Yeah, it makes sense. Thoughts in general on, I see more contractors than not just using the diffuser as the balancing damper and not installing balancing dampers at the plenum.
Yeah.
Is that
not a fan? Yeah, it's for airflow control. It's much better done at the at the trunk duct. Something is better than nothing, but a professional HVAC contractor is going to have balancing dampers and is going to shoot for this 85. And I'll tell you real quick, if all those sharpshooters out there, if they did the math and they add up all these, I guess I've stopped sharing.
No worries. No, I'm still seeing your screen.
Okay, good.
Well, I mean, but it's just showing black. It says end of slideshow, click to exit.
Oh, maybe that's what, let me do this. I must have bumped hit something. But if you add up all those numbers, it's going to add up to more than our design airflow. And the reason is because some of these rooms have a larger cooling flow than heating flow. In the wintertime, they don't need as much heat. They need more in the summer. And so this is so we're sizing for that largest flow.
Gotcha. Again, I had an inspector in a presentation I was giving the other day, or a ex-HVAC contractor. Long story short, he's like, oh man, my designs do that. My designs are so good, I don't need balancing dampers. It works out perfect every time. I don't ever have any comfort problems because it's all engineered on the front end. Is he magic or is he full of it?
That's pretty impressive. So, if you can take a duct slide rule and look at what a 6-inch flex or a 12-inch piece of pipe can deliver over a range of static pressures. I will say that when I began using computer-generated, computer-calculated duct sizing, the need to balance the airflow diminished greatly. Most of the contractors listening will know that typically it's going to be this little, what was this? I think this was a closet. No, this is a mechanical room. That duct is going to need to be balanced. This bedroom branch run is going to need to be balanced. This kitchen, this dining room. So you know pretty quick that the leads coming that are the shortest will need the most attention. But when it's been calculated per run, as a lot of software does, then that really cuts down on the need to go back and balance. So I think there's some truth to what he said. That he never has to balance. That's a rather encompassing statement. But I'm, hey, if he did, more power to him.
Let's get to some questions. In reference to Windows internals, I've got a couple on Zoom, and then I've got a few more sent in otherwise. So I've got about 8 questions. Since we're running almost an hour over, Wes, I will double your fee that I'm sending.
Good.
Be looking for that check. It is in the mail. In reference to Windows internal shade, does the shading cover 100% of the window area as a default?
Right, and the default is 50%.
Okay. One of the biggest culprits to manual J.
Share my screen if you want to put something up. Great. If not,
I don't think so. We'll throw this up just because.
Okay. Well, and
that was one of my favorite pictures. I say if that's R8, that's okay. That's definitely usable. So let's look at the rest of these questions. Where'd my question pane go? Doggone it. Oh, there it is. One of the biggest culprits to manual J accuracy I have seen are window values, not overhangs. Verifying if they are within code and accurate is important also. These values are also hard to get sometimes. I would think they're more important than overhangs, which are important as well, of course, just not more. That was more of a comment than a question, but.
Well, that is a great comment. And I think that whoever made that is exactly right. And I think that in some instances the code committee was working a little bit in the dark. And I think feedback from code officials on things like this is extremely helpful. So by all means, check that NFRC data and make sure that the solar heat gain coefficient matches, or that the U values are lining up. Absolutely. Jason, I think you mentioned at the beginning, this isn't meant to be the be-all, end-all. By all means, feel free to supplement on your plan review. This was meant to provide a basic tool for the folks that are out there helping support doing things right.
Okay, and just a few more sent in.
Yeah.
Multistage and VRF advantages for high latent loads.
Yeah.
Are those that would be
Right.
that would be helpful for removing high latent loads, correct?
Could be. Again,
Necessarily.
I think there's a lot of folks out there with a lot of promises, and I'm not going to say that they're not true. I'm just saying, show me the performance data. Once I see how this system performs at certain conditions, then I know. But if I'm reading a very glossy brochure that makes some claims, I don't have a lot of basis for evaluating the factual accuracy of what's being said. Hand me performance data, and now at least I have something a little more concrete, a little more solid to work from.
Had somebody ask, in your opinion, what are some of the easiest way to game the one-page form? And is there any, just check all the items for plan review and inspection, or what are some things that are gamed?
The easiest way to game it. Yeah, the easiest way to game it is just to throw some numbers on there, hand it in, and see if anybody cares. Anybody can write anything on a form. I hope this isn't a revelation to some new code officials out there. And that's so at the very least, if someone gamed it and they just threw numbers on the page, handed it to you, and you stuck it in the file, at the very least, you've got documentation. This contractor said these were elements of the design that I used, and if it becomes necessary to double check what was used, then you can pull that piece of paper out and say, well, this isn't accurate. This doesn't match up with what the house does. This doesn't align with the manufacturer's performance data or the duct layout or any of those things. So, it's easy to game, but that's why we threw a few things up here that we believe could be quickly, easily verified, and or provide supporting information so that you could investigate further if you so desired.
That's one. This was my favorite thing on these design and review forums. I don't know if you're a Simpsons fan as well and notice this, but when you put that in the building file and don't look at it at all and see that the contractor was Bartholomew J. Simpson, he might have just been throwing numbers in there. I love that.
Glad you caught
Wes,
that.
you noticed. Yeah. Oh yeah. Good. You need to go. You should have just gone out and take credit for all this. You didn't have to give the committees and stuff credit. I mean, when somebody gives me credit that I don't deserve, I'm quick to just go ahead and keep my mouth quiet. You're much humbler than me. I give you credit for that. Okay, 2 more quick questions, then we're done. How long does it typically take, in your opinion, to do an accurate JS&D?
Yeah, the short answer is it depends. So there are some tricks of the trade. I would build templates. If I'm seeing 2x4 construction with R13 in the walls and something in the ceiling and slab on grade, I would already have those ceiling and wall assemblies. If I'm typically seeing windows from a certain manufacturer with certain U values or certain heat gain coefficients, solar heat gain coefficients, I've got those templates built. The tricky bit is the survey. I did room by room heat loss, heat gain calculations. So you got to get your ruler out and collect the data and plug it in. There's some tools that facilitate that much more so now, so that they'll read things, or they'll have draw functions that let you create these dwellings or represent the models of the dwellings. And it depends on the house. Am I dealing with a 2-story, 5,000 square foot house? Am I dealing with a 1,200 square foot ranch? I got where I could drive up on a change out, drive up to a house. It's a nice rectangular ranch, and do the heat loss, heat gain in like 20 minutes. And then I was so familiar with the equipment I was selling. I knew the performance data. I knew what capacities there were. And if I'm not saying I had it memorized, but I had a good ballpark, and then I could look it up. Hey, this, I knew my design conditions. I knew what I was expecting for the entering air condition, et cetera. And you've got a reference right there. I had a catalog, as a matter of fact, and pull it up. Boom, there's the equipment. Duct sizing on a replacement, not a big deal. On a house coming up out of the ground, then you need to look at the framing details if those are provided. Sometimes you can glean some aspects from the elevation drawing, other drawings, and see what things are going to happen. See if there's electrical, what you might have to dodge. But JS&D, again, I hate to, I don't want to be too wishy-washy on this, but it's tough to just throw out a number. Professionals that do this are very efficient and very proficient, and I'm sure there's some guys out there that can do it a whole lot faster than any number I throw out there. And I think there'll be some guys who are learning, and by golly, that first load calc takes them all cotton picking day. And sometimes that's the way the pickle squirts.
Well, and that's what, as we talked about earlier before everyone hopped on. I mean, ideally you're doing it all yourself and you know it in and out, but there's always an option. There's third-party companies that will do load calculations, equipment selection, analysis, and duct design for you. Yeah. And as a builder, if that analysis and design requires you buy a 2.5 ton unit instead of a 4 ton unit, well, you've more than offset the cost of having that professional design and calculation done.
Yeah. Yep. Absolutely. No, I agree. I would much rather see the work done by someone who's not the installing contractor than not done at all. I think that there's always risk. I make an assumption that the person selected knows what they're doing and they're being rigorous and that they're following the rules. And just as there's a wide range of HVAC professionals, there's also a wide range of professionalism in the design community. But I think that the truth bears out over time, and you'll be able to ascertain who's walking the walk.
Well, we are 45 minutes over. I'll ask Mariel if she can adjust the ICC CEUs and add another 30 or 45 minutes. Sorry we ran over, but when you have somebody like Wes willing to share their expertise and knowledge with you, the last thing I want to do is cut them off. If it was just me talking, we should have finished 20 minutes early. Thanks so much for joining us, Wes. I really can't thank you enough for adding your expertise and insight.
Blessed.
And I'll probably be reaching out to you for a part 2 on those illustrated examples if you're willing. So you can probably go ahead and block my emails now.
Yeah, sure.
Thanks again. Thanks for joining us, everyone. Look for the course evaluation for your ICC CEUs. And any way I can help you out, don't be afraid to ask. Y'all have a great day. Thanks a lot.